Hello and welcome to this section of the Physics 3 tutor. In this section we're going to continue where we left off in the last section talking about magnetic fields, and specifically we're going to continue where we left off and start talking about the force exerted by a magnetic field on a particle or on some other charged object. So we know that that's the other half of the equation. Just like the electric field, we have a field that's generated, and then the other half is we put something in the field and watch how it moves. That's the Coulomb force, right? So here there's obviously going to be something as well. We know magnets push. We know there's a force. So what is the force, right? Let me go ahead and write that down. Let me just write it down, and then we'll talk about it, because it takes a fair amount of brain cells to understand it, but it's not that hard. The main thing to remember is the magnetic field B, that's how we're labeling it, only exerts a force on moving, I'll underline that, charges within the field. Now think about that for a second. Magnetic field B only exerts force on a charge that is moving within the field, or a force on moving charges within the field, right? That is totally and completely different than electric field. Electric field, I said, hey, there's a electric field here, put a charge, let it go, zoom, charge zooms off, and it gets pushed along the field lines, in the direction of the field lines. Magnetic field is different. If you have a magnetic field right between me and you, and if I put a charged particle right in that field and let it go, absolutely nothing will happen. There is not going to be any force. It's not going to push that electric charge. That's the truth. That may go against your intuition based on your magnets, right? But that's how it works. And I'll circle back in a minute and teach you why the magnets behave the way they do in a second, but you have to trust me. If there's a field, if I have a magic field generator in the floor, and between me and you is a bunch of magnetic field lines, right? And I take a proton and I stick it right there and I let it go. Proton will not move. There is no force on that proton. That force from the magnetic field on the proton will only arise if that proton begins moving. So, to take another thought experiment, if we have magnetic field between me and you, right, from my little field generator in the floor, right, and I take an electron, and this time I zing that electron where it begins to move. I give it some motion. At that moment, okay, now there's a magnetic force pushing that electron, curving its path, changing its direction, right? That's when the magnetic field springs up. It only happens if the charge is moving. So you see there's a real interesting duality here. The magnetic field itself is only generated by charges that are in motion, and forces only act on particles that are moving through the field. So the key thing for you to think about, if I had to tell you one thing, is for magnetic fields you should think motion. You should think magnetic fields involve motion, because it's true. The only way they're generated is if I have electrons or protons moving, or some kind of charged object moving, right? And then once I have the field generated, if I put another test charge in there, the only way there's ever any force acting on that guy is if that charge is in motion relative to the field, right? Totally different than the electric field. The electric field is generated spontaneously even if the particle's at rest, right? And if I put a test charge in the field, a force pops up even if the charge is at rest. Whereas the magnetic field is only dealing with motion. So obviously there's some similarities. There's field lines, there's forces, but there's significant differences between electric and magnetic fields and forces, right? So without further ado, let me show you what the actual force is on a charge that is moving, because it has to be moving, inside of a magnetic field. The force on a charge Q moving, because it has to be moving, remember, in a magnetic field, not M, in a magnetic field B. That's what we're writing down here. What is the force acting on this charge moving in a magnetic field B? That force, we're going to call it F sub B, because it's a force due to the magnetic field B, is equal to the charge times the velocity, it's a vector, so I've labeled it that way, crossed with the magnetic field B. This is not a multiplication. This is not 3 times 4. This is a vector cross product, right? And this vector is the velocity of the particle in motion. And this vector is the field. That's the field strength and the direction. So don't get too worried about that. I mean, if you're rusty in vectors, go back and review vectors. But basically, don't forget, a vector has a strength, a magnitude, and a direction. And obviously, the strength and the direction, the magnitude and the direction, are both going to be important anytime you calculate anything when you have a field. If the field points this way, it's going to act differently on the object than if the field points this way. Field is stronger, it's going to act differently than if it's weaker. So this equation looks quite simple, deceptively simple, but it really has tons of information. What we're basically saying is that the force due to this magnetic field depends, forget about the cross product, it depends on the strength and the sign of the charge that's moving in the field, right? It depends on the velocity of the charge, and it depends on the magnetic field. So this V is the velocity of the charge moving through the field. This Q is the strength in coulombs and the sign of this charge in the field. This magnetic field is the strength and the direction of the magnetic field. All right, so let's just forget about the fact that it's crossed for a second. We're gonna get there in just a second, but just think for a second. Note that if I increase the value of this charge, then the force due to the magnetic field increases. Like if I hold everything else the same, forget about the cross product, we'll get there, okay? But if I increase this charge, then you can see they're all basically multiplied together. There's a cross product here, but that's a special kind of multiplication. If we increase the charge, the force increases. If I increase the velocity of that particle moving through the field, then the force on it increases, right? And if I increase the magnetic field, if I make it stronger, then the magnetic force increases. So at first glance, this equation makes sense. If I make the charge stronger, then it's going to be pushed harder when it goes through the field. If I speed it up and make it go faster through the field, then I'm going to have a stronger force acting on it. And if I increase the field strength itself, I turn my magnetic field meter up, or my magnetic field strength up, then I'm going to have a stronger force on it as well. And I'm going to write a giant but down here. So these are all true, but there's one very important thing that's staring us in the face because this is a cross product. And I'll write it down and we'll discuss it. FB, which is the force acting from this field, does not speed up or slow down the charge Q that's moving through the field. It only changes the direction that Q is moving. Let me write one more thing down, and then this will be absolutely clear. Why is this the case? Let me write why. It's because when you look at this guy, what do we have? It's because FB acts perpendicular to the velocity of the particle and the field. I've got a ton of information on the board. We need to make sure we understand it. When you look at this, this is a cross product. What does a cross product mean? It means you have two vectors, right, in space. I'll draw a picture in just a second to make it absolutely clear. But you have two vectors in space. Think of arrows, right? When you have a cross product between two vectors, that means literally you take your right hand, remember right hand rule? You cross one vector into another one. The resulting force, in this case the force on the particle, is actually acting perpendicular to its velocity and to the magnetic field. What this means is this force does not push the object along its velocity, right? It doesn't push it, it doesn't speed it up. It acts perpendicular to its velocity. So if the object's moving this way, it's totally conceivable that the force from the magnetic field pushes it into the chalkboard. So as the guy moves this way, the force is going to curve it this way, right? Because it's actually pushing it perpendicular to its velocity. So it's not going to speed it up or slow it down, it's just going to change its course. And that comes expressly from the cross product. Now this stuff isn't made up. It's not like somebody said, oh, it's a cross product. It's because we observe it. If we go put a magnetic field in a bottle and shoot some electron beams in there, those electrons don't speed up or slow down, they just curve. They just turn directions depending on how the magnetic field's oriented and how the beam is oriented. They just turn the direction of it. That's totally different than electric fields. Electric field's not like that at all. If I stick a charge right here, we said it over and over because I was trying to prepare you. If we stick a charge right here, the force that comes from this interaction pushes it in the direction of the electric field line. It speeds it up, right? Or it could slow it down depending on the sign of the charge and the sign of the electric field and everything else. But it basically pushes it along the direction of the field lines. Whereas this guy, it only pushes it in a direction perpendicular to its velocity in the magnetic field. So that is the reason why it doesn't speed it up, it doesn't slow it down, it only changes direction of Q is moving. The reason is because the force is acting perpendicular to the velocity and the field. Now, let me draw a picture because a picture will actually help us quite a bit. All right, so before I draw the picture, let me just rewrite this real quickly for you. The magnetic force B, you're going to memorize this. QV cross B. Don't forget your vector symbols. Remind you this is a vector. This is a force. This is a charge. This is a velocity. This is the magnetic field. All right, let's draw a couple of pictures, and this will be a lot clearer. All right, let's say that I have a magnetic field. Again, I have some generator in the room here, and this magnetic field is going up. Now, in reality, there's lots and lots of arrows going up, and in reality, they're all closed loops. So they're coming around and all that, but I'm just drawing a very small segment of a magnetic field in a room. So I'm not drawing the whole loop, I'm just drawing a part of it, right? Now, right here, let me change colors. Right here, at the sort of this location, I have some I have some charge Q. Now, if we just stopped right here, and if this charge Q were not moving, then I have lots of magnetic field lines, it's sitting in a field, Q is not moving. We already talked about the fact there's no magnetic force. You can see that from here. Q would be a number if we have two coulombs of charge, but if the velocity is 0, the cross product, even if you work out the cross product, if V is 0, then the whole force is 0. So there's no force acting on a charge that's not moving. So if we did this, there'd be no force, right? But obviously that's not a very interesting problem. So what we're going to do is we're going to say that this charge is actually moving this direction with velocity V. This is sort of a three-dimensional drawing, so I've got to imagine 3D space here. All right, so think about this particle. It's kind of zipping along. Right when it gets to this point, we take a picture and we look at it and we say, hey, it's got a pretty big velocity moving this direction. It's got a pretty big magnetic field moving this direction. How is this magnetic field going to interact with this? Well, it's QV cross B. V and B are vectors. You're taking the cross product. So you take V, cross it into B, the magnetic field B. So you take your right hand, you cut into V because V is first, you cut into V, you cut into B because that's second, and then you see that this magnetic force is going to be pushing it basically out of the board. Since this is a three-dimensional drawing, the way I'm going to draw it is basically like this. This is FB. So use your imagination. This is a three-dimensional thing. If you have B and you have a velocity going this direction, you cross them, then basically you can see that this force acting because of the field is basically perpendicular to the other two. This is 90 degrees. This is 90 degrees. Everything's 90 degrees, right? So you can think of a sheet of paper being in the plane of B and V. This is a plane. This force is acting 90 degrees perpendicular out of that plane, and it's always going to be that way. The force is always going to be coming out of the plane that contains your velocity and your magnetic field, right? So if we take another snapshot like 2 seconds later after this interaction happens, then basically, let me go ahead and kind of draw it again over here. Let me draw it here. This is the magnetic field we had. Then what's going to happen? More or less, obviously this particle, we took a snapshot at this point, but it continued on. What's going to happen? Well, the particle was coming in, it was coming in, it was coming in. It gets this force that begins to kind of curve it. like that, basically. I'm just going to stop drawing it because I'll end up screwing up the shape of it. But basically, it's curved motion, because this force does not push along the velocity it's moving, doesn't speed it up. It just changes the direction. So you have to kind of, if you were going to really look at it, you'd have to sort of simulate it. It would change the direction, then you would recalculate the cross product with the new velocity to see which direction the force is going to be. Then you calculate it again every second or so. If you were going to write a computer program, you'd go every second through the motion, and you would say, okay, it curved its path this way. Okay, now the velocity direction is different. Okay, so how's the force going to act in the next second? And you keep doing it second after second, and you would see a curved path pop up, right? So that's that. Let me draw one more example. I try to do things obliquely. Sometimes people enjoy that. Some people can't really visualize that. So let's visualize the magnetic field instead of an oblique view like this. Let's imagine it a top-down view of a magnetic field. Top-down view of something similar. Let's say we have these dots represent magnetic field B. This means they're coming out of the board. So you're not looking from the side anymore. You're looking like top down, basically. So here is your magnetic field. Because I have dots everywhere, the magnetic field's actually pointing at you, straight towards the camera, right? Now in this field, let's go ahead and say, down here, let me replace this one. Let me say we have a charged particle Q, and let's say we give it some initial velocity in this direction. We'll call it V. So you're looking top down, bird's eye view, magnetic field is coming toward you, and you get a gun or something and you shoot an electron or something up through this guy. Let's say, for the sake of argument, it's a positive charge. So it comes up like this, right? It's a positive charge. And how do we find the direction? What's going to basically happen, qualitatively speaking? Well, we take Q, V cross B, V cross B. So we have to cut into V first, and then we cut into B. Now don't forget, you have to have these vectors tail to tail whenever you do the cross product. So this vector, the magnetic field's coming out of the board, you got to imagine a vector sitting right on top like this, right, with its tail down here and its head up here. So it's coming towards you, and if you want to do the cross product, you go V cross B. So let me put this paper down for a second. So here it is. I'm going to cross it, right? I got to go through V first, I cut through it, and then I cut through B. My force is actually going to act in this direction, right? So when I do that, if I took a snapshot a few seconds later, I probably would see this motion. I want to change colors. I probably would see this motion look something like that. Because I shoot it in like this, and as soon as it interacts with the field, the force begins to push it and bend it that direction. So I've tried to show you with a couple of kind of qualitative examples that the direction that this force is acting is always perpendicular to these two guys, and you can see the plane of B and V lies here. The direction of the force is perpendicular to that. It's perpendicular to the velocity. It's perpendicular to the magnetic field. Now, the direction also depends, obviously, on Q. When you're using this vector form of the equation, Q can be a positive charge, and that's what I've drawn here. Q is a positive charge. It's going to go this way. If Q is a negative charge, then everything is reversed, and it basically, if it's a negative charge like an electron, it bends the other direction. It goes the other way. And you would find that out if you did the actual cross product, because everything would be negative. So you do this cross product, you get an answer, and your Q would be negative. So that would basically flip the sign of the force totally opposite direction. So when we're drawing these pictures, I'm assuming positive charges in Q, but just note that if you flip the sign of the charge, then the force is going to be mirror image opposite of what it is. So that's sort of another neat thing, and that kind of makes sense with the electric field as well. For an electric field, the force also was dependent on the charge magnitude and also the charge sign. And the same thing here. Obviously, the force is dependent on the charge magnitude, but the direction of the force is also dependent on the charge sign. So we've covered some very important topics so far. We've talked qualitatively. I really believe big in you understanding what you're doing conceptually, right? If you don't get anything else out of this, you at least understand the big picture, right? So now what we're going to do is talk about the units of the magnetic field. What units do we use in the SI system? Then we'll wrap this section up, and off in the next section we'll work a couple problems to get you comfortable with how this might actually work in a real-life test situation. So for now, let's talk about the units of the magnetic field B. All right, the units. So, the SI unit of magnetic field B is Tesla. And we denote that with a T. Now, a lot of you have heard of Tesla coils. There's even a car, the Tesla car, right? Tesla's a pretty famous name. Well, he did a lot of work with magnetic fields, so the unit is named after him. Now, there's also something you may have heard, for those of you who study this a little bit ahead of time. There's an older unit of B that's called a Gauss, right? And we denote that with a G. But it's, we don't really use Gauss too much anymore. We use the Tesla unit because we're all dealing with the SI system. But just so you know, 1 Tesla is 10 to the 4 Gauss. So the unit of Gauss is actually much, much smaller than the unit of Tesla. I only bring this up because if you're working in a lab and you have a magnetic field meter, sometimes you'll see it labeled in Tesla, sometimes you'll see it labeled in Gauss, but it's measuring exactly the same thing. Now let's give a couple of examples. I like examples. Earth's magnetic field B is on the order of 10 to the minus 4 Tesla. Right? So it's not like this insanely crazy strength magnetic field, right? A typical electromagnet. An electromagnet is like a high current, basically, that flows around a metal core. And that current generates a magnetic field. The metal core concentrates a magnetic field, and you get a giant magnet out of it that only works when you turn the electricity on. That's called electromagnet. So if you look in a junkyard where they're lifting up the cars with electromagnet, that's a really strong electromagnet. Something like that would be on the order of 1.5 Teslas. So you can see how Tesla is a pretty large unit. I mean, even a really strong magnet is 1.5 Tesla. And then just as a final comparison, a small bar magnet, like you might play with at home, is 10 to the minus 2 Tesla. So you can see from this that a small bar magnet, relatively speaking, is actually stronger than the Earth's magnetic field. But don't forget, though, that's a little misleading because the Earth is enormous, right? The Earth is enormous, and for it to still generate any kind of measurable magnetic field is hugely impressive. And obviously there's a lot of energy because there's so much volume in that magnetic field that we have in the Earth, right? Tiny little bar magnet might be pretty strong, but ultimately the volume of it and the physical dimensions of it is so small that it's not really as impressive, so to speak. So don't look at these numbers and think that, think anything more than that. I just wanted to give you kind of a general overview of what kind of things we're talking about magnitude-wise of what we see in nature. All right. Now there's one final thing I want to tell you, and that is that when you're working problems, you don't always have to use that cross-product version of things. Let me rewrite this again. The magnetic force, just to make everybody clear, FB is QV cross B, right? And just to make sure everybody understands, the force that you get out of that is in newtons. The charge you put into this is in coulombs. That's what C is. The velocity you put in is meters per second. Of course, this is a vector, so it's got magnitude and direction. And the magnetic field that you're using in these calculations is Tesla, because that's the unit of magnetic field. So make sure you're using those things. Now, in real life, this is the holy, this is the holy grail, so to speak, of the equations that you're going to use. This encompasses everything. It encompasses the charge, magnitude, and strength. It includes the direction and magnitude of both of these vectors, right? So if you have all that information, then you would literally crunch a cross product every time and get an answer. However, a lot of times in your physics problems, you don't really need to go through all of the motions of doing a cross product, because a lot of times you don't really care necessarily what direction the force is. Maybe the problem only asks you, what's the strength? What's the magnetic force in newtons? Maybe the problem doesn't even ask you what direction it's pushing the guy. Maybe you only care about the magnitude. Maybe you only care about the direction. So this is obviously what's always going to work. But if you only care about the magnitude of this force, then the magnitude of the magnetic force would be written as magnitude of this guy. And basically, you do the following. It's the same thing that you learned in basic physics. Q, V, B times the sine of the angle between these two vectors. Now let me just write down, just so you know, phi is the angle between V and B, the vectors V and B, right? So this is handy because a lot of times you don't really want to crunch a cross product if you're just trying to find the magnitude of something. Basically, any cross product can be written as, forget about the Q for a second. If it were just V cross B, you've learned from your trig and your calculus that the magnitude of that vector, if you just forget about Q, it's V, magnitude of V times magnitude of B times the sine of the angle between them. That's what I've got here. This is magnitude of V, magnitude of B times the sine of the angle between them. The Q is just sitting out in front almost like a multiplicative constant. It just kind of hangs out in front. The real action is happening here, right, as far as the cross product action. Why is it a sine? Because when these two guys are at 90 degrees from each other, in other words, if I have a vector here and a vector, here, 90 degrees, then you're going to get a maximum from your force because the sine of 90 degrees, or pi over 2 radians, whatever you want to think about, is 1. Right? As you start to shrink the angle between your velocity, like let's say this is velocity and this is magnetic field, as you shrink it, then the magnitude of this force goes down, 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 down. And if you line them up perfectly, if you actually shoot a particle in the direction of the magnetic field, right along the field line, so there's actually no angle, then there's absolutely no force. So if we had a magnetic field line this way, like this direction, and I get an electron gun and I shoot it directly across the field line, not across, directly along that field line, exactly perfectly lined up, then that electron will sail on through and nothing will happen. No forces will happen because V cross B, there's no cross there. There's no angle between them, and that's how cross products work. That's why we use a cross product here. So when you're looking at the magnitude of this guy, then you're going to be talking about the angle between the guy, the two vector fields, the magnitude of the magnetic field, the magnitude of the velocity, and also, in the case of this, when you only care about the magnitude, you're only going to care about the magnitude of the charge as well. So if you're working a problem where they only care about the magnitude of the force, you don't really care if it's positive or negative. You don't care what direction anything's happening. You just want to know that angle, and you do a quick multiplication. I mean, this is 4 things multiplied together, and you're done. So when you're doing your problems, remember that. Don't overwork the situation. If you've given a 3-dimensional vector and you're trying to find out exactly what direction everything's heading, then yeah, you got to do a cross product. If you're given a problem where everything's lined up properly and you just want to know what the force is, you don't need to do a cross product. You just use the magnitude formula, but these are basically, this guy comes directly from this. I'm Jason with MathTutorDVD.com. I hope you've enjoyed this lesson. Make sure and watch it a few times. Most of all, what I really wanted to do was provide a nice compare and contrast between electric fields and magnetic fields, because studying them separately doesn't do them justice. Really, they're two different things with lots of similarities and lots of differences. And what we'll learn later is that the way they behave when they come in contact with one another, that you can coax them into forming a wave, electromagnetic wave, that can carry energy through space, through empty vacuum, is truly an amazing thing. There's lots and lots of stuff we don't understand about electric fields and magnetic fields. Really, we've conquered the how, right? We can describe what's happening. As to the why it's happening is much, much deeper than this. I mean, why does the force look like this? Why is it perpendicular, right? Well, that's a question that's much, much deeper. So don't feel like physicists have all the answers, because we don't. But, you can learn the elementary stuff and build up your knowledge, contribute when you yourself get to that point, and make sure and just really understand the fundamentals here, because that's really what's going to help you as you work through your physics courses, and for those of you going on into research, into helping us understand how this stuff really works on a really detailed, fundamental level.